Okay, so the next one is 15, and in this one we are given f to be the field of real numbers. Now we have to prove that if phi is an automorphism of f, then phi leaves every element of f fixed. In other words, here we have to prove that the field of real numbers has only the identity mapping as an automorphism, or in other words, that the automorphism group of the field of real numbers is the trivial group. So let's see the solution. Now in this solution, what we are going to do first of all is we will consider one positive real number, apply this function phi to that real number, and then see what we get. Solution: let x be a real number such that x is positive. Then we know that x has a square root, in fact 2 square roots. Now that fact we are going to write like this. Then I am going to refer to this result actually. Lemma five six five from Terence Tau's analysis book. X is equal to y square for some real number y. Now this is of course just simply the fact that any positive real number, like here x is a positive real number, has a square root, and that square root is y. Actually there are 2 square roots, y and minus y. Now I am giving this reference. You can use some other reference from some other book where you may have come across this result, or you can just simply take it as something that we already know. In fact, it is something by now it has become quite standard that positive real numbers have square roots. Square roots exist for positive real numbers. So that's what I have used here, but because I used this book, so I am giving this reference. Okay. Now if I apply phi to x, that means I am applying phi to y square, and because phi is a homomorphism, being an automorphism means it's a homomorphism, so it in particular respects multiplication. So y square phi is the square of y phi, and this is a square, the square of a real number. That real number is y phi. So a square of a real number is a real number that is always non-negative. It cannot be negative. It is either 0 or positive. But in this particular case, we will get it positive. Why? And the reason is this. Note that phi is injective, that means 1 to 1, and being a homomorphism, the image of 0 under phi is 0, that means the real number 0. Why does this imply this thing? That's because you see our x is non-zero. Now if we somehow take this to be equal to 0, that means x is being mapped by phi onto 0, but already 0 is being mapped by phi onto 0 as well, and because x is non-zero, so then the injectivity of phi or its one-to-oneness will be violated. So that is why this cannot be equal to 0, but it has to be non-negative, so it has to be strictly greater than 0. In other words, what we have managed to show is that if we apply our automorphism phi on a positive real number, then we again get a positive real number. And now we are going to use this fact very nicely to show that the mapping phi is actually an order preserving mapping on the set of real numbers. Like this, if R1 and R2 are two real numbers such that R1 is less than R2, then R2 minus R1 is a positive real number. And so if we apply phi on it, then by what we have proved just now, that phi image will also be a positive real number. And so R2 minus R1 phi is also positive, and we can in fact conclude other things from this. Because phi is a homomorphism, still that fact is there. So this thing is R2 phi minus R1 phi, that is greater than 0, or R2 phi is greater than R1 phi. That means if R1 is less than R2, then R1 phi is also less than R2 phi. In that sense, it is order preserving. It keeps the, if the numbers are in this order originally, then their images are also in that corresponding order. And note one more thing, that here we do not need to assume about, say, the signs of these real numbers. Each one of these real numbers can be positive or 0 or negative, anything it can be. The only thing we are using is this order, and that's how we are getting a positive real number, which is their difference, R2 minus R1. Okay, so now we have established that phi is order preserving. Okay, now with this new information, what else can we say about phi? Our aim is to show that phi actually does not change anything. If you apply phi on a real number, then you are going to get that real number back. That is, phi is the identity map. Okay. Now, suppose the that is false. Suppose the negation is true. Suppose that the image of R under phi is not equal to R for some real number R. And we are trying to get to a contradiction from this supposition. If we manage to show that there is a contradiction, that means we will be forced to conclude that R phi is equal to R for every real number R, and that's what we want to show. Then, by the trichotomy property of the ordinary order relation on the system of real numbers, if this is the case, then either this is greater than R or less than R. Let's choose any one of these inequalities, say this one. Let R phi be greater than R. Okay. Now we are going to use the property which has a name of real numbers, that the set of rational numbers is dense in the set of real numbers. And what that says is that between any two distinct real numbers we can find a rational number. That is, we cannot get rid of rational numbers inside any interval of real numbers. No matter how small an interval you choose of real numbers, you will always get at least one rational number there, and hence infinitely many. So that property also is something that is already known from either calculus or real analysis, but still, because we are referring to things like this from Gauss analysis, so here also I am going to write one such reference. By proposition 5,4,14 tau, I can write here, no? R phi is greater than Q, which is greater than R, for some rational number Q. In fact, this denseness property of the rationals inside the reals is a consequence of the definition of the real numbers itself, or rather the construction of the real numbers, I should say. Whether you use the Cauchy sequence construction of real numbers or Dedekind's construction, this property is a consequence of that itself. Okay, for some rational number and it's a very useful property, this denseness. This denseness tells us that using the rational numbers we can approximate any real number with as much accuracy as we want. But anyway, let's not get into those analytic discussions. Let's do algebra. Okay, so now what? Now note that we have already seen what an automorphism does to the rational numbers in the solution to exercise 12, in this solution set itself, I mean in this section itself, that any such automorphism does not change any rational number. So an automorphism of the set of real numbers or the field of real numbers already fixes all the rational numbers. This is something we already know. Okay, so we are now going to recall that. How should I write this? We have already seen in the solution to exercise 12 that 5 fixes every rational number, and this fact in turn is in fact a consequence of the fact that 5 fixes 0 as well as 1, the real number 0 as well as the real number 1. We have discussed about this when we solved exercise 12. So now the fact is that phi fixes all rational numbers. So phi will fix this rational number q as well. Hence, so combining this fact that phi is not going to change q, along with the other fact that phi is order preserving, you now apply phi on this inequality q greater than r. Doing that, we get this q equal to q phi that will be greater than r phi. Q is fixed by phi and phi preserves the order. So q greater than r means q phi is greater than r phi. But now see what we have got. Q is greater than r phi, yet r phi is greater than q, and this of course is a contradiction. It contradicts the law of trichotomy in the system of real numbers. So we just simply write a contradiction. And this contradiction arises from this inequality. A similar one would arise from this one. A similar contradiction arises from this other inequality, r phi less than r. So that means we have no way to go. We have come to a dead end, provided we are sticking with this supposition. So that means the supposition should be wrong. So the last supposition is wrong. That is, phi must fix every real number. So that's just what we wanted to show. Next, exercise 16. It has two parts. There is something very interesting about this exercise. Let's just first go through the solution and then we will discuss. Find all real quaternions t equal to a naught plus a1i plus a2j plus a3k satisfying t squared equal to -1. and then there is part B, which is a start exercise for a t as in part A. That means a real quaternion t whose square is -1. Prove that we can find a real quaternion S such that S inverse TS is equal to I. No, it's not S inverse. We can take S inverse TS, but it's not given like that in the text. STS inverse is equal to I. Okay, so let's start. So we just have to work with this equation. That means we have to calculate t square. So let's first calculate t square. So that means we now have to use that awful quaternion multiplication, because we want to calculate t square, but as we will see, it's not that bad also. If you use the fact that the quaternions form a ring, they form a division ring in fact, where only that law is not true, that multiplication is commutative. Everything else is true. I mean, that is only missing, which would have made it a field. So if we use that distributive law and everything else along with those rules that ij is k, jk is I, and so on, then we can easily calculate t square. So let's just do that. We have, so first we calculate just t square, and then we will impose the condition that t square is -1. A0 plus A1I plus A2J plus A3K. It's better to write two factors like this so that we can see what we are doing. Okay, so let us continue from this side. These black smudges I could not avoid. Somehow they keep reappearing. Anyway, so this would be equal to, first we multiply this by A0 using the left distributive law. So A0 square plus A0 A1I, A0 A1I plus A0 A2J. The first one is easy because it has only A0 or A0 plus A0 A3K. Then we multiply this thing by A1I, but now we have to be careful. A1I A0, which is the same as A0 A1I. Then A1I A1I, A1 square I square, but I square is -1, so minus A1 square. Then A1I A2J, that means A1 A2 IJ, IJ is K, so plus a1 a2k, then a1i a3k, a1 a3 ik is minus j. You can remember that by considering this thing, no? ijk, ij is k, jk is I, and ki is j. And if you go in the clockwise direction, all the things will come in that same order but with a minus sign. ji is minus k, kj is minus I, and ik is minus j. So now we have, see, I lost track of what I was doing. We have already completed multiplying with a naught, 1 2 3 4. Now we are multiplying with a1, 1 2 3. So now I have to multiply this with this. So a1 a3 ik. So ik means going the opposite direction, so minus j, minus a1 a3 j. Next by a2j, a naught a2j, a naught a2j. Next this one, ji, ji is minus k, and a1 a2, that means minus a1 a2k, minus a1 a2k. Okay, next this one just like multiplying this two, this one is going to give us minus a2 square, then this times this, a2 a3 jk, jk is ordinary I, plus a2 a3 I. Okay, then by this one, plus a naught a3 k, ki is j, a1 a3 j, plus a1 a3 j. Okay, then this times this, kj, kj is minus I, that means minus a2 a3 I, minus a2 a3 I, and finally minus a3 square. So what do we have? Finally we have a naught square minus a1 square minus a2 square minus a3 square. Let's just first write those things. A naught square minus a1 square minus a2 square minus a3 square. Okay, so this part we have got. Then what about, I think there are some cancellations going on, right? For example, those terms which do not have a naught, I mean the cross terms not having a naught. For example, a1 a2k, that should get cancelled with something, although I don't see anything. a1 a2k, oh, it's just below this, a1 a2k minus a1 a2k. Okay, so this two plus and minus, so they cancel out. Minus a1 a3j plus a1 a3j, plus a1 a3j minus a1 a3j, these two cancel out. What else? Plus a2 a3i minus a2 a3i, they also cancel out. So what are we left with? A naught a1i, another a naught a1i, a naught a1i plus a naught a1i, plus 2 a naught a1i. Okay, a naught a2j plus a naught a2j, plus 2 a naught a2j, then a naught a3k plus a naught a3k, so another term plus 2 a naught a3k, and I think we have taken into account all the terms. The squares we have already written here and everything else. So this is t square. So now let's impose the condition that t square is minus 1. Okay, and let's see what we find. T square should be minus 1. Okay, now t square is minus 1 if and only if this thing is minus 1, that is this real quaternion is minus 1. Let's write it once more. Minus a3 square. Ultimately it has come out in a nice form which is somewhat manageable. a0 a1i plus 2 a0 a2j plus 2 a0 a3k. This is equal to minus 1. Now by the definition of equality of two quaternions are equal if and only if their corresponding components are equal. So by that we get these equations: a0 square minus a1 square minus a2 square minus a3 square equal to minus 1, and this should be 0, this should be 0, and this should be 0. That means 2 a0 a1 is equal to 2 a0 a2 is equal to 2 a0 a3 is equal to 0. So that means t square is minus 1 if and only if these conditions are true. Now everything depends on a0 being non-zero or being 0. So let us see what happens if a0 is non-zero. Okay, that condition must be seen. What happens in that case? Now if a0 is not equal to 0, then from these equations what do we get? Let's not forget the fact that now we are dealing with real numbers. All these four quantities that we see, a0, a1, a2, a3, they are real numbers. So these are just ordinary equations with real numbers. So if a0 is non-zero, 2 is already non-zero, then these equations give us a1, a2 and a3 all should be equal to 0. Then a1 equal to a2 equal to a3 is equal to 0. But then, but this implies we can write the reason for these smudges when I try to erase things is that the board is never fully dry. There's enough humidity to cause this situation. That is the problem. We can't get rid of humidity here in this state. We are in the northeast side of India, so that's why this problem. But then what happens to this first equation? If a1, a2 and a3 are 0, then we are getting a0 square is equal to minus 1. This, however, is not possible for a real number a0, which is not possible. So we must have so that means this cannot be the case. A0 has to be equal to 0. But then you do not get anything from these equations, but you do get something from this equation. Hence, so that just simply means what? A1 square plus A2 square plus A3 square should be equal to 1. If that condition alone is true, and of course A0 is 0, then t square is minus 1, and conversely if t square is minus 1, then A0 should be 0 and the square of these three things A1, A2 and A3 should be equal to 1. That's why I am using double implication. Thus, the set of all real quaternions whose squares equal minus 1 is, we are going to write it as a set, is this, and the quaternions look like that. That is, in them the if I call it the scalar part, the first real number is not there. A1i plus A2j plus A3k, that's how such a quaternion would look, and additionally this condition should be true, plus A3 square is equal to 1. Now, why was I saying that this question is interesting? It is interesting because you see, what does this equation tell you? This equation tells you that t is a square root of minus 1. Okay. And you can understand that the field of complex numbers is embedded inside the real quaternions. If you look at a real quaternion like this one for example, A0 plus A1i plus A2j plus A3k, a quaternion has 4 components, right? A0, A1, A2 and A3. If these two components are 0, then you get A0 plus A1i. And if you carry out the multiplication of quaternions on such symbols where you have only this part and this part, you will see that it matches exactly with your multiplication of complex numbers. So the complex numbers are a part of the system of quaternions. Now, if you further restrict yourselves to this part only, A0, that means you are just considering real numbers. Within that system of, within that restricted system, which geometrically represents the line, there is no square root of minus 1. When you jump from that line to the plane, when you jump out from that system, you go to the extension, which is the system of complex numbers. Geometrically, it's the plane. Then there are two square roots of minus 1, I and minus I, the imaginary units. But now, these are the square roots of minus 1 in this 4-dimensional system, which you cannot think of geometrically, but it's a 4-dimensional number system. It has 4 components. In this, these are the square roots, and you can understand that there are infinitely many square roots of minus 1 in the system of real quaternions. So that fact is somewhat very unusual, that from having no square root of minus 1 in the system of real numbers to having exactly 2 in the system of complex numbers, then the next jump is enormous, that is having infinitely many. And I leave this fact to you to convince yourself how the fact that the square roots of minus 1 are forming this set make this set infinite. Okay, that you have to understand on your own. So let's now go to part B. So this is a strange fact about quaternions, that there are infinitely many square roots of -1. Now this next part B asks us something else about such square roots. That for any one of them t, we can find a real quaternion S such that ST S inverse is equal to I. And that thing is like this. Part B. So now our t is one such t, that t square is -1. So by part A, that is already given. So by part A, t is equal to a1i plus a2j plus a3k, where a1 square plus a2 square plus a3 square is equal to 1. In order to see that this set is infinite, you just have to understand that infinitely many such triples of real numbers are there, where the sum of the squares of the components equals 1. But anyway, now we have this. Okay. Now, if a1 is equal to 1, is that how it goes? If a1 is equal to 1, yeah, in place of a1 we can take a2 or a3 also. Anyway, let me just I mean, whatever I have written here, if this is correct, let me see what we get. If a1 is equal to 1, then what do we get from this equation? a2 square plus a3 square then should be equal to 0, because this a1 square and 1 you can cancel from both sides. But then a2 and a3 themselves should be equal to 0. So we write then a2 is equal to 0 is equal to a3, and so what happens to our t? a1 is 1, a2 is 0, a3 is k. So our t is equal to I, and we want to find a quaternion S such that ST S inverse is I. So in this case we can just choose S equal to 1, because that's the easiest choice. In this case, we can choose S is equal to 1. Why we are considering this a1 equal to 1 case separately, now we will realize. Now, suppose a1 is not equal to 1. Now consider the real quaternion The problem is that if I apply too much pressure to erase these smudges, it will only make them more permanent. Quaternion So now we are going to consider one special quaternion. S equal to, I have something here, let me see if it works. I say let me see if it works because I found it a while ago and I forgot whether it really works or not. 1 minus a1, I did not get the time to verify this though. Okay. Now let us calculate the product ST. Like how we would calculate normally a product of two quaternions. Now ST is going to be what? A3 divided by 1 minus, you can understand why we need a1 not equal to 1 here, because we have this term in the denominator, plus a2 divided by 1 minus a1i plus j times our t, that means our t is that t, a1i plus a2j plus a3k. Let's see what happens. And we also should not forget that we have this one also. So let us now carefully multiply these two. This times this. So that will be a1 a3 divided by 1 minus a1i plus this times this plus a2 a3 divided by 1 minus a1j plus this times this. Plus a3, that means a3 square. A3 square divided by 1 minus a1k. Yeah, now let's be more careful, because I times I, that is going to be I square, which is minus 1. So minus a1 a2 divided by 1 minus a1. Minus a1 a2 divided by 1 minus a1, then this times this, ij is k, so plus, that is just plus because ij is k, a2 square divided by 1 minus a1, a2 square divided by 1 minus a1 k, then this times this, ik is minus j, ij ki, ki is j but ik is minus j, so that means minus a2 a3 divided by 1 minus a1, a2 a3 divided by 1 minus a1 j. Okay, and then finally we have to multiply by j. Ji is minus k, so minus a1k. J is j square, which is minus 1, right? That means minus a2. Okay, a2 has come out alone. Anyway, let's see what happens. Jk is I plus a3i. Now let's gather the like terms together. So first let us consider the constants, means the terms which lack I, j and k. That means this one and this one. So minus a2 minus a1 a2 divided by 1 minus a1. This is the first thing. And then what about I? With I think we have only this one, no? This one. So let's just write this a3i then j. For j also we are having only one term. I think something has gone wrong, no? Either I have considered this s itself, this s does not either work, or I have made some mistake here. Let me just simply see once more. a1 a3 by 1 minus a1 I, okay. a2 a3 by 1 minus a1 j. Oh, okay. I forgot that I have these things here. See, that's why I thought that I have only one I here. How foolish. Plus, we not only have one I here but an I here also. Yeah, now it seems okay. a3 plus a1 a3 divided by 1 minus a1 I. See how quickly we make mistakes. This is one I, this is another I. Next j, this one and that one. So for j, I think j terms are getting cancelled, no? a2 a3 by 1 minus a1 j minus a2 a3 by 1 minus a, yes. So we need not worry about these two. They cancel out. And we have what else? Only k terms. And in k terms we have three terms. This one, and this one. So writing them carefully here, a big plus, and then minus, let me write this one first, minus a1, then plus a2 square divided by 1 minus a1 plus a3 square divided by 1 minus a1 k. Yeah, now it's okay. Okay, now it's time for simplification. This times this, so minus a2, I am not taking any chances now, I will do everything, plus a1 a2 minus a1 a2 plus a3 minus a1 a3 plus a1 a3 divided by 1 minus a1, and this is I, plus we have only k term. So here what we are getting, 1 minus a1 minus a1 plus a1 square plus a1 square plus a2 square plus a3 square. Okay, so now these two cancel out, so we are having minus a2 divided by 1 minus a1 plus a3 divided by 1 minus a1 I plus, okay. Now this sum a1 square plus a2 square plus a3 square is 1. We already have that condition because that is the type of t we are considering. So we actually have 1 here, and that 1 minus a1 divided by 1 minus a1 gives us 1. So that means we just simply have plus k. Okay, so we have got something. So this is our ST, but this is not just any ST. It's not just any quaternion. It's a special type of quaternion. And the thing is that if we go back to our original S, we can then write it like this. You see, now I am going to write things as little bit differently. I write this one first, and then I write plus A2 divided by 1 minus A1 I squared. Okay, because I squared is minus 1, so I will get a minus 1 here, plus Ij, because Ij is k. Okay, now note carefully that I can take I common out, or in other words, that is just a casual way of saying that this is equal to the product Is I times A3 by 1 minus A1, A3 over 1 minus A1 plus A2 by A2 over 1 minus A1 times I plus j. And this is nothing but our original S. A3 over 1 minus A1 plus A2 over 1 minus A1 I plus j. Yes, that is what we have proved is that ST is equal to IS, since S is non-zero. S is a non-zero element, that means it's a non-zero real quaternion. Why is S non-zero? Because this is S, no? And this component is non-zero. So that's why S is non-zero. And a real quaternion, if it is non-zero, it will have a multiplicative inverse, because the quaternions form a division ring, a skew field. So inverses exist for non-zero elements. So now you just multiply on both sides from the right by S inverse, and then that's it. The above equation gives us STS inverse is equal to I. So that means my old calculation is actually true, thankfully. So that's it. That's the solution, and it ends this section also. In the next section, which section is it? I forgot. I think in the next section we have an application of these ideas in the geometric, in the part of Euclidean geometry where we deal with constructions of figures using straightedge and compass. We will see. Okay, so that's just it for tonight. So the next upload is of course tomorrow, and because we have already gone through Galilean group theory exercises, Galilean ring theory exercises, so tomorrow let's again do group theory exercises from Lee's algebra. So see you with that tomorrow. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.